Okay, hey everyone. So, in this video, I'll be discussing a review for test one. So, test one is, it's going to be open for 2 weeks. So please, 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 before I even start this, make sure that you don't just take the test right away, without studying, without using that time to your advantage. Remember, the tests are an extremely large portion of your final grade, and there's no redos, nothing like that. So you really want to make sure that you go into these tests fully, fully, fully prepared, um, and get yourself started off on a really good foot in the class. So it'll be 10 questions. Feel free to use formulas. Um, I really don't have anything against, in this environment, just letting you guys, have the formulas available to you. So you can have a formula sheet while working on the test. But of course, you do have to know how to use the formulas. That's, 99% of the work. 10 questions, and pretty much nothing. Actually, nothing from chapter one is on there. Chapter one is kind of just like an overview of statistics. There was nothing like super, super um, important there. Nothing really to be tested on there, I should say instead. So the test just focuses on chapters two and three. And so let's go ahead and start off with what kind of stuff from chapter two do you have to be on the lookout for? So, number one, you have to know how to make a frequency distribution. And of course, I've got here, well, this is just our notes. So, of course, please feel free to use those to study. Of course, to construct a group frequency distribution, we've got the procedure right here. So it's very good, step-by-step procedure. Remember, the really important thing here is when finding the class width, that I've got this little message over here on the right. You have to round up, basically no matter what. Even if it's a whole number, you round up to the next nearest whole number. That's to ensure that there's enough room in every class for all of the data. So when finding the class width, remember you divide the range by the number of classes that are asked, which is told to you. You never have to decide that in the questions. You have to make sure to round that number up always. Okay, there's, a lot of good examples here in the notes as well. And there was plenty in the homework, and the quiz as well is good to study from as well to get more practice there. You could always just redo those questions, to get extra practice and study from. So please make sure to use those as well. Okay. So we also, of course, after processing the data a bit and getting it into a data distribution, a frequency distribution, I'd say, rather, sorry. We can also then further view the data, get a better idea of the data through images such as histograms, frequency polygons, ogives, things like that. So, definitely make sure that if you have a frequency distribution that you can then make a histogram accordingly. Of course, cumulative frequency, it just adds up everything below a certain value. So cumulative just means everything up to the point that you are evaluating to, up to and including, not just the class you're looking at, but the class you're looking at and everything before that as well. So it's everything up to a certain value. And So the important ones I would say histogram, frequency polygon. I guess knowing ogives is important because cumulative frequency is very important. It does talk about cumulative frequency in there. There might be a question there on the test for sure on that. No pie charts. Definitely a dot plot though, I think, as well. And then, yeah, I think that's pretty much it for chapter 2. Let me think a sec real quick. Okay, so another thing I'm going to post is the homework solutions from my previous in-person statistic classes, which you guys can also use as another resource as well. So I just pulled it up to make sure I don't like forget anything, to just have a brief look at these questions. Yeah, so these are just making things into frequency distributions, more frequency distributions, frequency distributions. Okay. Relative frequency, that's just the percentage, essentially. If anything's asking you about a relative frequency, let me pull up an example, maybe. Let me pull up 37. So in this particular example, there were 28 data values, and the frequency is, what percentage of the data values is taken up by that class. So all you have to do is divide the frequency by the total number of data values to get the relative frequency, just the percentage amount of times that data values occur in that class. So, for example, in this one, right, I did 8 over 28, 11 over 28, 2 over 28. The total is always going to be the denominator of those. And then just a couple constructing histograms, frequency polygons, ogives, things like that. Did I ask more here? Oh, yeah, a lot more. Holy jeez. Forgot how long I made this homework. Vertical bar graph, it's just literally sideways. It's just another histogram, so there's no need to really get into semantics there. A Pareto chart, if you ever see a Pareto chart, all it does is it's a bar graph that puts everything in descending order, but I'm not going to put one of those on the test. Okay. So I think that's good for chapter 2. And then let's go to chapter 3. That's a really, really big chapter. A lot of stuff from here is going to be on the test. Probably, this chapter probably is going to be like 70% of the test, where chapter 2 is probably like 30%. So definitely make sure I would study chapter 3 the most, I would say, for sure. And practice that one the most. Okay, so the first measure that we learned, remember section 3.1, this was on measures of central tendency, what happens around the middle of a distribution. And the first measure that we defined, of course, is the mean. The formula for mean is the same whether you're dealing with a population or a sample. Remember, when dealing with a population, a lot of the symbology deals with Greek letters, mu, sigma, things like that. Whereas when dealing with a sample, it's always English letters like X bar rather than mu, S rather than sigma for standard deviation, etc., etc. So that's just to help kind of let you know what framework you're working in, whether population or sample. If you ever see this symbol in a formula, this is capital sigma. It means sum. sum up all of those values. So, for example, the mean here, which is x bar, the formula is the sum of all the x values, x1 plus x2 plus x3 plus all the way to xn. If n is 5, it would be x1 plus x2 plus x3 plus x4 plus x5 divided by, and then n would be 5 in that case. Remember, n is just the total number of data values. So it's nice that the formula for mean doesn't change whether it's a population or a sample. It's just you add up all the data values and you divide by the number of data values. It's just the average, right? That's how to calculate an average. You add them all up, divide them by however many there are. It's definitely not a hard one to remember, but definitely one that you need to know. Big N is the population size. Little n is the sample size, but n is the size of whatever it is, regardless. And then we looked at some examples of coming up with the mean, and there's plenty of examples in ALEKS, of course, as well. And then we have a separate formula for grouped data. It is the sum of all the frequencies times their midpoint divided by n. So what you do is first you find the midpoint of every class. Remember, the midpoint is just essentially the average of those 2 points. So you add them up and then divide them by 2. Right? To find the middle, you add the low bound plus the high bound, and you divide by 2. That's the midpoint. So that's what's referred to as xm in the notation here. And then f is the corresponding frequency. And then, of course, the capital sigma means add all those up. So you take the first frequency times the first midpoint plus the second frequency times the second midpoint plus yada, 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 all the way until all the classes are done. And if I guess sometimes n is not explicit in these examples. It is in this one because it says there are 25 total CEOs in the distribution. But if it doesn't give that, another way to find the number of data values in the distribution is you just add up all the frequencies. And that's why I've got here n is equal to the sum of all the frequencies, in case they don't give it to you. And then just did an example here with this one. So that's mean, right? It could either be for raw data or already grouped data. We still have, if we only have the grouped data, we don't know what the raw data was. We don't have all the data values. It's not exactly right away apparent how to calculate the mean. That one's a little bit not as intuitive and not really as widely known as the other ungrouped mean formulas. So definitely make sure to remember or have that on your formula sheet. Then another relatively important measure of central tendency, not as important as the mean. The mean is really probably the most important one, is the median. The median is the midpoint. So it doesn't really tell us much about the entire distribution, whereas the mean takes the entire distribution kind of into play. The median just looks what's happening in the very, very middle of the distribution. And there's 2 different ways to find it. If there's an odd number of data values, it's very, very easy. It's just there is a middle value, and you just find it. It'll have an equal number of data values on each side of it. Whereas when there's an even number of data values, you've got to average the 2 middle values. There's going to be 2 values that have an even number of, well, essentially you can cut it directly in half where there's an even number of values to the left half and to the right half, and you have to average those 2 middle values closest to the divider, essentially. The mode is the one that appears the most often. There can be more than one mode. If they appear the same number of times. And then the mid-range is the lowest value plus the highest value divided by 2. It's the median of the range. The range being... Well, I guess I shouldn't put it that way. Let's just leave it like that. The lowest value plus the highest value divided by 2. That's the mid-range. Okay, and then we come to the weighted mean, which looks difficult. Looks scary. But it's not so bad, especially if you do all the work in like tables and charts and the like. And the formula for weighted mean, it's the sum of all the weights times their data value divided by the sum of all the weights, which is what we've got right here, right? You take the weight of the first data value, you multiply it by that data value. You take the weight of the second data value, you multiply it by that data value, add all them up, that's your numerator. For the denominator, you just add up the weight of the first value, the weight of the second value, the weight of the third value, all of them, add them all up, and then you calculate that value. So the weights, sometimes it's hard to tell what are the weights, what are the data values. The weight is like the percentage of that data value. How do I explain this a little better? Let me pause a sec. I have to gather my thoughts on this one. So the weight is basically how much that class or data value is worth, I guess is a good way of saying it. So, for example, English and Psych are not worth as much as Bio. And they're worth, like, how much they count toward your credits is their worth. That's kind of like their weight in this example. So definitely remember this formula. A really good example is like a GPA, calculating the GPA. Or was there any others here? Let's see. What's another? So I pulled up the homework, the homework from my in-person class here for those questions. Here, 55 is a GPA example, right? Their grade, again, is the data value, whereas the percentage that they're saying there, that's their the weight in those. In 56, the costs of helicopters. It's asking for the weighted mean of the costs of all the models. And so in this case, the weight would be the number sold, and the cost would be the data value. Something like nutrition and things like that. In this example, using the weighted mean, find the average number of grams of fat per ounce of meat or fish that a person will consume over a 5-day period. Let me think for a sec. So which one is the like amount of how much we're getting of that thing? That's the ounceage. For example, the fat doesn't change, right? Fried shrimp is always 3.33 fat per, I don't know what that stands for, gallons per ounce or something. I don't know. And so that doesn't change, whereas how many ounces we get of that thing does change. So that's kind of how you discern what the weight is there and what is the data value. Because I know that can be definitely tricky for sure. Okay, then section 3.2. This is when we're talking about measures of variation. So we're talking about not a single data value. We're talking about the entire distribution and how much does the data vary within that distribution. Is the data clumped or is the data spread out? how clumped or how spread out it is what variance is trying to figure out. I think I meant to put range in the last section. That's not measure of variation, actually, so that's in the wrong section, I think. So this is where we come up with what's called variance and standard deviation. Variance and standard deviation are the main measures of variance, of how spread out the data is. So, a very high sigma means that the data is spread out a lot. A very low sigma means that the data is not spread out, aka clumped together, right? If you have a data set, which it's just all 10, right? That data is not spread out at all. It's just one data value. It's very clumped. It's as clumped as you can get. There, the standard deviation would be 0. You could even measure it yourself. And so, the size of that number tells you how spread out the data is. And we use it in a lot of important calculations to help us figure certain things out. So these formulas, very, very important. Have to know these, have to know how to use them to calculate variance and standard deviation. There also is a formula for sample variance and standard deviation as well. The only difference is the denominator changes to n minus 1, and the notation changes around, but the formula difference is that it's n minus 1 rather than n. And in the questions on the test, I'll always very explicitly state if it's a population or a sample so that there's no confusion on which formula you need to use to get it correct. So again, definitely have to memorize these ones and have to know how to calculate them. So practice, double check, triple check to make sure that you can come up with these using your calculator. Okay, so again, very, very important that you are able to get those numbers on your calculators. If you're trying it on your calculator, you get a different number than what the correct answer is. You've got to make sure you're doing the order of operations correctly on your calculator. If you just do each operation and then hit enter, it's not going to come out right. You've got to make sure that you're feeding to the calculator the right order of operations. And we've seen examples there as well. And then we've got this horrible formula for finding those same numbers when the data is grouped rather than when the data is ungrouped. So the formula is not fun, definitely not easy to memorize. Again, definitely make sure you have this formula. Remember, xm is the midpoint of that data value. F is the frequency of that class. F is the frequency of that class. N is the number of data values. This one's really, really hard to plug in correctly and not mess up on. So definitely just make sure you get a ton of practice before going in and taking that test. And I had an example here that we did. Okay, so Chebyshev's theorem. This just gives us a minimum number that must fall between a certain number of deviations away from the mean. So remember, the mean is always right in the middle of the distribution. I should have a picture somewhere, yeah. The mean is always right in the middle of the distribution, and the number of standard deviations away from the mean that you're going is however many, is like the low bound and the high bound of the data values that you're looking for the percentage of, however many fall in there in the distribution. So, for example, if k is 2, that means we're trying to use Chebyshev's theorem to figure out the minimum percentage of data values that fall within 2 standard deviations away from the mean. And in this case, we see 75%. So I go 2 standard deviations to the left of the mean, 2 standard deviations to the right of the mean, and that is the boundaries for where 75% of the data falls between. That's what Chebyshev's theorem gives us a minimum percentage for. And remember, the formula is just 1 minus 1 over k squared, where k is the number of standard deviations away from the mean that you're looking at in each direction, of course. Did another example here, 3. I drew this one a little funky because I wanted to drive the point home that Chebyshev's theorem is for all distribution shapes, regardless of whether it's normal or not. And so 3 standard deviations away from the mean, notice now it's a higher percentage of data values. Of course, that makes sense, right? The more standard deviations we go away from the mean, the more of the data we're capturing, so the higher the percentage is. The empirical rule is when we know that the shape of the distribution is normal. What does normal mean? That it's bell-shaped and symmetric. So if you go straight down the mean, half the data values are to the left of that mean and half are to the right. Has to be 100% symmetric. And these numbers are always the same if you know that it's normal. It's 68, 95, 99.7%. I highly encourage you to remember those numbers. And we've done examples. We'll look at the formula a bit later. For now, you really just want to memorize these numbers. The formula is not nice to come up with these percentages. Very ugly, actually, so it's not a nice formula like 1 minus 1 over k squared. So rather than use the formula for when we know it's normal, we generally just try to remember these 3 for now. And we looked at some examples. In this example, we do that the mean was 26.8 and that the standard deviation in this case was 4.2. We want to see what percentage of Americans would expect to consume more than 31 pounds of citrus per year. Pretty tough question here. Let's just go over this one again. We go out 1 standard deviation from the mean. We see, that's where that 31 that they're looking for is. It's actually the upper bound of 1 standard deviation. And it's asking what percentage of Americans would you expect to consume more than that amount. So we were able to fill this in according to the empirical rule. The 68% that we had in the middle, remember, according to the empirical rule, when we go 1 standard deviation away from the mean, it encompasses 68% of the data. That's how I got that 68. Then there's 32% left to divvy up, right, amongst the left tail and the right tail. Well, due to symmetry, we know that they have to have an equal amount, so we cut that 32 in half, giving us 16 and 16 on each of those tails. Now that we've got the percentages of the distribution filled in, we can answer the question of what percentage of Americans would you expect to consume more than 31 pounds of citrus fruit per year. That's the number to the right of 31, everyone to the right of 31, aka that 16% that we found. And that would be the measures of variation. Really important stuff there. Let me pull up the homework from my in-person class for Chapter 3 real quick. I think we looked at 3.1, did we? I don't remember, actually. Yeah, we did. Yeah, I remember. Yeah, we looked at those. So 3.2, again, it's asking us to calculate those measures of variation. So we've got to find the range, variance, standard deviation, all that stuff. A lot of good examples here. So plenty of good examples to practice. Here's a grouped example. Remember the grouped formula, really, really, really annoying one. So you definitely want to get good practice there. There's a couple good questions here that you might be able to try. Chebyshev's questions, which we discussed. Okay. And that's an empirical rule question because it's saying you have to know what the distribution looks like when it's bell-shaped and when it's not bell-shaped. So when it's not bell-shaped, Chebyshev. When it is bell-shaped, empirical rule. And then we come to the last section. 3.3, measures of position. And so in this section, it's trying to tell us about where a specific data value lies in a distribution. Is it at the high end of the distribution? Is it at the low end of the distribution? And it also allows us to compare two completely different distributions, allow us to compare where a data value lies in each of those and how they relate to each other based on, remember, that value called the z-score. Okay, so for measures of position, we've got the z-score. That's really, really important formula. It's x minus the average over the the data value minus the average all over the standard deviation. It's the same whether it's a population or a sample. And the z-score very conveniently relates everything in standard deviations away from a mean. So for a z-score of 0, let me look at this picture here. A z-score of 0 is always right at the mean, right? Remember, the number stands for the number of standard deviations away from the mean it is. So if it's 0 standard deviations away from the mean, that means it's on the mean. So the z-score of the mean is always 0. And then you go out 1 standard deviation in each direction, 2 in each direction, 3 in each direction, and you've got those 3 numbers. The 68, 95, 99.7, respectively. And for example, in this question, we were comparing a test score in 2 completely different classes that had 2 completely different grading scales, and we were still able to see which one had a better relative score based on whose z-score was better, right? It seemed in this case that in geography, they had a z-score of 1.83, while in accounting, they had a z-score of 1.71. So they're further to the right of the average in geometry, which means, a better score than they are in accounting, which is a 1.71 z-score. So z-score, very important. If you want to know things about where a specific data value lies in a distribution, and maybe compare it to some other distribution where some other data value lies in it, that's what we use the z-score for. So very important formula. It ends up popping up a lot throughout the semester, actually. We use that a lot. It's very, very important. And then we also have percentiles. Percentiles divide the data into 100 equal groups. And there's 2 methods with percentiles. Either we have a data value and we're looking for what percentile does that data value fall in. Is it in the 99th percentile? Is it in the 1st percentile? Is it in the 71st percentile? Where is it? And that formula is right here. The first thing we need to do for that formula in order to use it is we need to sort the data, because the first parameter here in that parentheses, it says, is the number of data values below x. So we have to sort the data, pinpoint where x is, and then count the number of data values below it for the formula. And then we add 0.5 to that, divide it by the total number of data values, and then multiply by 100, and it will tell us what percentile they fall in. And if we have, if we know a data value lies in a specific percentile, and we want to figure out what that data value is represented by, what data value falls there, we've got this other formula. We still have to order the data from lowest to highest. we find this number c, which is n times p over 100, where p is the percentile that we've been given. And then we ask ourselves this question here. There's two possibilities: either c is a whole number or it's some decimal. If it's a whole number, we count that many data values from the left, and that's our data value that we want. And if c is a whole number, we take the average of that number and the one higher than the cth number. So we take the cth number and the cth plus 1 number. So if c was 10, we would take the 10th number and the 11th number in the data in the distribution and average those, and that would be our answer. We did a couple examples there. And then hold on. Okay, so quartiles, on the other hand, divide the data into 4 equal regions. And, excuse me, when finding where the quartiles are, the first thing you want to do is find Q2. That's the one right in the middle. It's just the median. Oh, well, first you have to sort the data. Sorry. First you have to sort the data. Then you find Q2. It's just the median. Then you find Q1 and Q3. Q1 is the median of the left half. Q3 is the median of the right half. So not that bad to find those. And then we've also got interquartile range, which is just Q3 minus Q1. We need that to help us find outliers, if there are any. And so to find outliers, you have to use the IQR. It's Q1, the boundaries is anything below Q1 minus 1.5 IQ times the IQR. The upper bound of outliers is anything above the high bound, which is Q3 plus 1.5 times IQR. So I drew a little picture here to help you better understand that as well. And had an example here as well. And that's all the content. Let's again check out that other resource I'm going to give you guys to study from. A couple Z-score questions here. A couple percentile questions. IQR question, Q2, Q1, Q3 question. Didn't ask about outliers, though. Same thing there. And then it's asking in this last question to check for outliers. And that's pretty much it. Again, it's a lot of material from Chapter 2 and Chapter 3, probably 30% Chapter 2, where we're organizing data and visualizing the data. So, making the frequency distributions, making the histograms, making the dot plots, things like that. Chapter 3 is where a lot of formulas are needed. Definitely make sure that you have a formula sheet for the test. You can't, it is on a lockdown browser, so you can't use the internet or anything like that while on there. So definitely make sure you write them down beforehand and have a sheet with you with the formulas that you might need. And again, for extra practice, you guys, again, I can't stress enough, the tests are a very, very, very high portion of your grade. You don't get a second chance on them. And you've got 2 weeks to study. So please make sure that you are fully prepared going in there. Make sure that you take the time needed to study all this stuff, and you can do really, really well. So I'm gonna post this homework from my in-person classes, which you guys can use as an extra study resource. Kind of like, give yourself a pre-test. Pick certain questions from here and see how you do. See if you get any questions wrong or anything like that. See what grade you would have gotten, what you need to work on, things like that. It's really, really helpful in math classes to give yourself pre-tests over and over and over again until you just know everything like that. That's how I would study math, and I think a really good way to do it. So I've got a lot of really good questions on here to give yourselves. I've got all the answers over here on the side, very detailed solutions, with all the formulas needed, all the pictures, everything, everything, everything. So really, really good resource. In fact, over here I've got a nice formula sheet with all of the important formulas that you might need. So that's in that. That'll be in that file as well, the homework solution file that I'm posting. Okay, so good luck on the test. Please make sure, again, to use that time available to you to study. Ask me any questions that you have beforehand. Don't take the test right away, the first or second day that it's available. Because if you end up getting a bad grade, you're going to be kicking yourself saying, oh my God, I would have had another week and a half to study and do so much better on this. Right? So just study, study, study. Email me with questions. Give yourself pre-tests and make sure you have a formula sheet and that you're good at plugging those in the calculators, and you should do really, really good on the test. And I wish you all the very best of luck. So again, please email me if you have any questions, comments, concerns, and good luck on the test.